So good afternoon to all in India and good morning or good day to all the participants from different parts of the world. It's a pleasure to welcome each one of you to this course by Professor Surdej on Introduction to Optical and Infrared Interferometry. You can read more about him in the links which have been provided in the forum, but he's one of the most distinguished, respected astronomers of our time, and it's a real pleasure and a privilege for us at IUCAA to be able to host this lecture, and we look forward to hosting more series of lectures by him in the future. And in addition to all his professional work, he has also been very actively engaged along with his wife Anna in outreach activities. We also have a pair of set of gravitation lenses which has occupied a pride of place in many institutions across the world, and we hope to sort of share those with you as well in the future. As far as this course is concerned, besides Jean, my colleague from IUCAA, Prakash Arumugaswamy, will coordinate it. And before I hand over to Jean, I would like to just say a few words about the Astronomy Center for Educators at IUCAA. This is a relatively new unit at the Inter-University Center for Astronomy and Astrophysics, and it consists of what is called a Teaching Learning Center, which is focused on improving and spreading the quality of astronomy education in the country, and also what is called the National Resource Center, where we are primarily right now making courses for teachers as part of the refresher courses. And as time goes on, we'll expand to more activities. And in the TLC, we are also trying to build a repository of experiments, design syllabuses at various levels. And I would welcome each one of you to participate in these activities by providing your inputs or even giving your suggestions or participating in the committees depending upon your level of interest and expertise. So I will close with these opening remarks. And one last point I would like to say is that our programs we'd like to emphasize really learning. So these courses are for learning a field or learning a subject from the best possible persons, whether they be located within the country or outside the country. And the emphasis is less on certificate gathering. If we do give certificates, it will be based on participation in the different processes that go on, whether it be quizzes, tests, assignments, whatever it may be. But the emphasis will always be that you learn something new from which not only you benefit, but from as teachers, also the communities you interact with, namely the students, also benefit. So with these opening remarks, I'd like to invite Professor Jean Surdej to start off. Thank you very much, Professor Jean.
Thank you very much. Good afternoon.
Sure, you have to move closer to your mic. You're not very audible right now.
Is it okay now? Can you hear me?
But you were better earlier.
I was better like this. Well, I didn't change anything. No? Okay, So good afternoon. Yeah, in India, where I special talks for many people I know who are located in Delhi, Nainital, Bangalore, Trivandrum.
Sure, you were a little better just a little while ago.
It's okay now?
It's better, but you were much better before the session started off.
I don't know what's the reason, yeah? Probably I didn't change anything in my setting, yeah?
Oh, this is perfect now.
Okay, perfect, yeah. And well, good morning and good evening, yeah, to all of you who are somewhere else, yeah, because I know there are people from all over, well, probably from all the continents, almost, except, Antarctica, of course, yeah. And well, of course, our best wishes is that you are all in good health, yeah, and feel well protected. So let me first say, yeah, IUCAA, and in particular, yeah, Professor Sekia, that you just heard a moment ago, yeah, so who's in charge, yeah, of organizing, yeah, the online lectures at IUCAA, and we propose to organize the present one, yeah. Well, thanks also to Prakash, yeah, for coordinating this nice activity, and to Santosh for the Zoom connectivity, which I hope is good everywhere, yeah. Now, a few words about the lecture notes, yeah. So the lecture notes, yeah, is a PDF document, yeah, to which you should be able to get access to, yeah. And these lecture notes were written after participating in September 2017 to the Every Schatzman School. It was organized in Roscoff, it's a northwest of France, and it was dedicated to high angular resolution imaging of stellar surfaces and their nearby environment. Yeah? So anyone interested in those proceedings, yeah, it should be possible, yeah, to get a handle on this. Yeah? Well, after that, we were invited in August 2018 by ISO to deliver in Paranal, Chile, yeah, lectures on optical infrared interferometry for the technical staff. Yeah? And the idea was that they could get, yeah, a more intuitive feeling about what interferometry is without, you know, caring too much about more tedious theoretical mathematical background. Yeah? Now, the background image that you see behind me is a picture that we took, yeah, when visiting the VLTI, so the Very Large Telescope Interferometer at ISO Paranal, Chile. And as most of you know, this nice facility allows to recombine, yeah, in a coherent way the light collected either by the 4 8-meter Very Large telescopes that you see on the background, yeah, and there are also 4 1.8-meter auxiliary telescope. Yeah. Well, if I set aside, you may see one of them, yeah, in the background. Yeah. And well, it is a very impressive instrument, yeah, composed of a very large number of subsystems. Yeah. For instance, each telescope individually, yeah, is supposed to track the stars. Yeah. Then you have the adaptive optic systems. Yeah. Then you have the delay lines, and all that involves a very complex electronics, mechanics, optics. Yeah. And we found that it was quite a miracle, you know, that such a complex system managed by, well, at least 100, yeah, scientists and engineers, yeah, may work at all, yeah, because of the high risk of any failure in one of those subsystems, yeah. So it's really very, very, very impressive, yeah. So it requires, you know, well, good skills, yeah, and a lot of competence and excellence, yeah. Today, you are also a few hundred participants, yeah, to this school, and I'm very much convinced that all together we may achieve, yeah, some nice endeavor. Yeah? And some of you will probably learn something, yeah, from the YouTube presentations, but I'm also certain that given the many, you know, different expertises served by all of you, yeah, in astrophysics, physics, yeah, instrumentation, yeah, science of material, optical fibers, etc., that each of us, yeah, may learn something from each other also, yeah. I mean that I should not be the only one to try answering some questions, yeah, but if any participants, yeah, knows a good answer to a question, yeah, I would invite him, of course, yeah, to participate very actively, yeah. Okay, now in November 2019, we were invited to deliver, yeah, a series of lectures at IUCA, yeah, in Pune. And this has been the results, yeah, of the series of videos that you may get access to via YouTube. Yeah? So they were videotaped by Anna, my wife, and edited by her and by Haniket, yeah? Also a member, yeah, of the IUCA team. Yeah? Now, let me share with you, yeah, our wonder each time we are visiting IUCA. Yeah? Well, Professor Narlikar, yeah, well, who is the founding father of IUCA, has set up, yeah, the most wonderful place that we know for stimulating new scientific ideas, yeah, fruitful interaction between scientists, students, yeah, and in a very nice atmosphere of tolerance, yeah, and very open exchange of ideas, cultures, everything, you know. So IUCA is presently managed, yeah, by Professor Somak Raishaduri, and I'm sure that many of you already visited the place and that you share this wonder. And I really very much hope, yeah, that those who didn't have an opportunity to go there, yeah, may do so one day. Yeah. So now interferometry, yeah, is about the art of recombining in a coherent way the light beams collected by either a pair of telescopes or by more telescopes. Yeah. And it's very likely that because of the very short notice, yeah, that you received, most of you didn't have the time, yeah, to visualize a YouTube video and the lecture notes, yeah. But this is not a problem. We have a lot of time in front of us, yeah. And I should say that these lessons, yeah, have been organized in such a way that they will take place over a very long time scale. So you may have, yeah, many opportunities, yeah, to visualize, yeah, them once or twice or even more, yeah, and then also to dream, yeah, about light interference, because you will see it's a wonder field of physics, yeah. So in this context, let me tell you that the two first lectures, yeah, will have a very intuitive flavor, yeah. So very, very little mathematics, yeah. And at the end of those two lectures, you should be able to construct your own interferometer and use it as a didactical tool, or also to perform, yeah, some basic measurements, yeah, like, well, setting a filament of a light bulb, yeah, some distance away, and well, using different baselines of your interferometers, yeah, to determine, yeah, what is the optical thickness, yeah, of the filament, yeah. Now, if you like too much, yeah, theoretical developments, yeah, you may stop there, yeah, after two lessons, yeah. There is no shame, yeah. And well, perhaps also the third lecture is quite accessible if you don't have a good background in mathematics. But if you already have a good background, yeah, I mean, well, knowledge about basic trigonometry, development of a function, yeah, as a series of Taylor, as a Taylor series, yeah, or also, well, some integral calculus, yeah, performances, yeah. You will have no difficulty to pursue, yeah, all the other lectures, yeah. And later on, yeah, we shall make intensive use, yeah, of the Fourier transform, yeah. And Professor Avinash Deshpande will also contribute, yeah, to this series of lectures by providing us, yeah, well, some good training on these transforms, yeah, and to show another approach, yeah. Well, it will be very rich, yeah. So this is a general introduction. Just raise your hands, yeah. If not, when or somewhat later, yeah. What I would do, I would just share my screen, yeah, with the lecture notes and just go through a few of the figures, yeah, of the first lessons, yeah, just to introduce you a little more to the subject, yeah. So if you have any questions, please raise your hand, yeah. Can you still hear me or not?
We can hear you, Jean.
Yeah. So that's good. Yeah, that's good.
They
yeah.
should be able to.
Yeah. So maybe what I shall do first, yeah, I will share my screen, yeah. Oh, ok, partager l'écran. Partager l'écran. Ok. Yeah. Times. Yeah. Yeah. Can you see my screen or not?
Not yet.
No, maybe take some time. Oh yes, I know why. It's because I have to. Modifier. Oh yeah. Yeah, I have probably to give special permission, yeah, before I can do that. Yeah. No.
No, I think you might have to restart share screen. Yeah, now we can see. But we don't hear you, Sean.
No, that is okay. This is my screen, yeah.
Your audio is suddenly very low.
Yeah. Can you now see
Yes.
the screen with the PDF file? Yes.
Yes, yes.
Correct. Yeah. So to all the participants, yeah, this is a PDF file, yeah, that you could get access to, yeah, and it presents the lecture notes, yeah, and well, I will just go through a few of the pictures, yeah, So first picture, yeah, shows a single aperture telescope, yeah? And it is very disappointing. Well, I suppose that I'm above the atmosphere of the Earth, yeah? And looking at a distant star. And what you see, yeah, is a dot of light, yeah? And the dot of light is a so-called airy disk, yeah? So it has a strange pattern, which is not at all associated, yeah, with properties of the star, yeah, but just with properties of the telescope, yeah. So it's a response function of your telescope, yeah. And it's very disappointing, yeah, that while looking at a star or still another star, you may learn nothing about, well, its size, about its mass, about its color, about its temperature, gravity, nothing. What you see is just a dot of light, the same when you look at all the different stars with the same telescope. Yeah? But now you see that the distant angular distances, yeah, between the two first minima in this airy pattern, yeah, well, as an angular size, which is proportional to the wavelengths, lambda, and inversely proportional to the diameter of your aperture. Yeah. So in radian, yeah. So you know that 3.14 radians, yeah, is equal to 180 degrees. So in radian, this angular size is 2.44 times the wavelengths divided by the diameter of your aperture. Now, if you go to a larger size telescope, like, oops, just jumping on this figure, you see that the diameter D2 is a bit bigger than the previous one. Well, you see that you still get an airy pattern, yeah, which is a signature, yeah, of your aperture, but not connected at all, yeah, with the physical properties of the star. And you see now that the distance between the two minima is smaller, yeah, yeah, because the diameter is larger, yeah. So the angular size, yeah, of the airy disk gets smaller, and this provides, yeah, a better angular resolution to your instrument. Okay, now this is if we look at a star, yeah. What if we look at a distant exoplanet, yeah? So let's assume that here is a view where we have an exoplanet discovered around another star, and we look at it, yeah, with our small size telescope. Yeah, we will see of this extended object, yeah, well, something which is not very clear, yeah? So you see it's fuzzy, yeah? But as you increase the size of your telescope, yeah, you may get a better view, yeah? And so that has been the dream of astronomers, yeah, to ever increase the diameter of the telescopes. And with present-day technology, yeah, the largest size that you may achieve is something very near to 40 meters, yeah? So, you know, you heard about the TMT project, yeah, about ELT1, etc. So there is a limitation, yeah, but fortunately, yeah, already in, well, at the end of the 19th century, yeah, Fizeau and Stefan, yeah, well, it's the following idea, yeah. If you take two individual telescopes separated, yeah, by the distance b, which is baseline, yeah, b like baseline, yeah, they showed that the angular resolution you could achieve if you let, yeah, the two beams of light interfere, yeah, is inversely proportional not to the size of each individual pupil, but inversely proportional to the distance between your two telescopes. Yeah? And this raised, of course, a big hope, yeah, that with such facilities, yeah, you could, you know, one day resolve angular diameter. Now, if you look, yeah, so now instead of seeing in the focal plane, yeah, the airy disk, yeah, well, you still see here, yeah, where is the central area of the airy disk, yeah. So which angular size is inversely proportional, yeah, to the diameter of a single aperture, but you see it's being crossed, yeah, by dark and bright fringes, yeah. And the angular distance between two consecutive bright fringes or two dark ones, yeah, is proportional to the wavelengths, but now inversely proportional to the baseline, yeah. And this is where you will get, yeah, improvement, yeah, in the angular resolution of your instrument, yeah, is that along the line joining the two telescopes, yeah, you'll improve your angular resolution, yeah, as you see it, yeah, on the dark fringes and bright fringes superimposed, yeah, on the airy disk. Yeah. So now in summary, if you look at a very distant exoplanet with a small telescope, you see it very fuzzy. As you increase the size of your telescope, yeah, it gets more clear. This is the hope, yeah, of the future TMT, ELT telescopes, yeah. But still, if you make use, yeah, of an interferometer, yeah, you may, yeah, very significantly improve, yeah, the clearness of your images, yeah, taking advantage, yeah, of the distance between the individual telescopes, yeah. And at this moment, yeah, the largest baselines which exist, yeah, are of the order of 400 meters with Shara. So you get an equivalent angular resolution, yeah, along a particular direction, yeah, equivalent to what you would get if you had a single dish with a 400-meter diameter in size, yeah. Now at ESO, well, the longest baselines, yeah, are of the order of 200 meters, yeah. Okay, now during these lectures, yeah, what we will show is that the images you get, yeah, of any extended object, yeah, is a convolution product, yeah, of the point spread function of your telescope or of your interferometer by the real image, yeah, of the object you're observing. Yeah? If you had a telescope with a diameter which is infinitely big, yeah, and this will never happen, of course, yeah, and we'll find out, yeah, how it's possible, yeah, to retrieve, well, a lot of information, yeah, in this image to which you cannot get access, yeah, by invoking, yeah, Fourier transform, deconvolution, etc., etc. Yeah. So, well, the subject of the lessons is something like that, yeah. Well, with a small interferometer that you will construct at home, yeah. Well, I will inform you how to do that, yeah, during the next lesson, yeah. You will try, yeah, to measure, yeah, the diameter of the filament, yeah, of this light bulb, looking at it with the interferometer, yeah. And astronomers do exactly the same with the interferometers. They are looking at very, very distant stars, yeah, with an interferometer and try to measure their angular size, yeah. Okay, now, once you are able to measure the angular size of a star, what can you do with that? Yeah, well, if you know, yeah, the distance to the star, and thanks to Gaia, yeah, the second release of data which has been provided recently, yeah, we have many estimates, yeah, of distances to nearby stars, yeah, thanks to the trigonometric parallax or proper motions, yeah. And thanks to that, yeah, if you multiply, yeah, the distance by the angular radius, you're able to determine, yeah, the linear radius of a star, yeah. And this is wonderful, yeah, already. But now, well, you know, most of the stars, yeah, well, are nearly radiating like black bodies, yeah. And we have, thanks to the Stefan Boltzmann law, a very nice relation between their effective temperature, yeah, the observed flux, yeah. Well, I would say bolometric flux, yeah, on Earth that you can get, yeah, with a photometer, and angular radius that you may get with interferometer, yeah. And here you have a fantastic way of estimating very accurately, yeah, effective temperature of. Well, in this first lesson, yeah, when you will visualize it, yeah, you will see that we represent the wave, yeah, with a certain function. Yeah. Okay, go on. Then we are tackling, yeah, the principle of Huygens Fresnel to understand, yeah, how an image at the focal plane of a telescope or of an interferometer gets formed. Well, but this is just intuitive. There is a I just say a few words about atmospheric turbulence, yeah? And of course, when you are doing interferometry, we are assuming that we have adaptive optics, yeah, at each single pupil to correct, yeah, for the atmospheric effects which are distorting, you know, the wavefront, yeah, which is a plane wave coming from a distant star. And during the first lesson, yeah, there is a little bit about the history of a measurement of stellar diameters, yeah, and first by Galileo, yeah. And I invite you, you know, well, any participant interested, yeah, in doing that experiment, yeah. So you may take, yeah, well, a wire, metallic wire, as thin as possible, you know, well, 1 millimeter would be fine, and you would put it vertically while looking at a distant star, yeah, which is very near to the horizon, yeah. Now you know that if you look well at the star and you're very far away, yeah, from the metallic wire, you will see the star. But as you set your eye closer and closer and closer, yeah, at a moment, yeah, the star will be occulted, yeah. And now by estimating, yeah, the distance between your eye and the wire, and while dividing the thickness of the wire by this distance, you will get the angular radius, yeah, under which you see the wire, but also the star. And this is what Galileo did, yeah. He estimated, yeah, the angular diameter of a star and found that it was probably about 5 seconds of arc, yeah, at that time, yeah. But what he was measuring, yeah, there was not an angular diameter. Yeah. What he was measuring, in fact, was a thin disk, yeah, from the location where he was observing the star, yeah. But it was already a kind of revolution, because before Galileo, yeah, the angular diameter of our eye, yeah, is about 2 arc minutes, yeah. And most of the people, scientists at that time, thought that the angular diameters of the star was of about 2 arc minutes, yeah. So this was already a nice progress to show that their size was much smaller. Now, well, another very nice way of estimating, yeah, the angular diameter of the stars is Newton. Yeah, Newton is a kind of a Beatles among the physicists. Yeah, because he, you know, just mentally, you know, he proposed a very nice way to estimate the angular diameter of the stars. Yeah, he said, well, look, when you look at the sun, yeah, its apparent magnitude is minus 26.7, and its angular diameter about half a degree, yeah, 30 arc minute. Now we said, well, let's assume that Vega, so a star of magnitude 0, yeah, is just a star like the sun, but at such a distance, yeah, that it is much fainter. So instead of having magnitude minus 26.7, it's a magnitude 0. What is the distance, yeah, to which I should set the sun so that it appears like a 0 magnitude star, yeah? And well, estimating, yeah, that kind of distance, he said, well, now I may find, yeah, what would be its angular radius, because I would just to divide 30 arc minutes or half a degree, the size of the sun, yeah, by that distance, and I would get the angular radius, yeah. And he found an estimate, yeah, of 2 milli-arc seconds, yeah. And this is fantastic, yeah. So you see that a theoretician, yeah, may do very interesting work, of course, yeah. Then comes piezo-type interferometry, and this will be the subject of the next lesson, yeah, next week. So you have 1 week, yeah, of time to visualize, yeah, the 2 first lessons, yeah, and well, already try, yeah, you have good guidelines in the second lesson on how to construct a mini interferometer, yeah. So try to do that, yeah. If you have any difficulty, yeah, you will raise your hand. We will have exchange interactions and find the solution, yeah, to make a reliable mini interferometer. Now, well, to those, yeah, who have the chance, the privilege, yeah, to have binoculars or a small telescope, yeah, what you could do is just to set, yeah, a screen, yeah, on your lens or just above the aperture, yeah, with two small holes, yeah, and you could eventually look at at Jupiter. Jupiter is visible at this time of the year, yeah. Well, probably not from India because of the monsoon season, yeah, but elsewhere, yeah. And you could try to find out, yeah, to which distance you should set the 2 holes so that, well, you will see the disappearance, yeah, of the fringes, yeah. But we'll come back to that, yeah, during the next lesson, yeah. So now you have plenty of time, yeah, to visualize the two first lessons, maybe to already construct, yeah, a mini interferometer just using some sheets of aluminium. Then you will need a needle, some glue, a piece of cartoon, that's all, yeah, and well, a lamp, yeah, and just a flashlight, yeah. Flashlight of most of the cell phones, yeah, would be adequate, yeah, to make the experiment, yeah. And well, I will be very interested, yeah, to read, yeah, with Professor Saikya, yeah, and with Prakash, yeah, already on the forum, yeah, whether you could obtain some results, yeah. But if you have any difficulty, yeah, we'll discuss it, yeah, during the next lesson, and you will see that well, light interference, yeah, is really something fantastic that you may dream about, you know, before falling asleep, and then sometimes you find, you know, new ideas, yeah, and well, it's always possible, yeah, to get new ideas, yeah, on in this field, yeah. So I will end my presentation now here and come back, yeah, to you. If there are any questions, yeah, you raise your hand.
So I request all the participants to just raise your hand and I'll unmute you so that you can ask a question directly. Or if you have any trouble with your audio, then you can post your question in the common chat window. Make sure you select the to field to everyone and set in your question, and we can discuss that here. I think we have a question from Sakshi Gupta. I'll try to unmute her.
Yeah, you know, I stopped sharing my screen and tried to get back to the video, but there's some difficulty. Do you still see my screen?
Right, no, we don't see your screen. We just see you.
Okay.
I think it should be fine now.
Yeah.
Let me. Sakshi, are you able to unmute?
Yeah. Yes, sir. Hello.
Yeah, you would have to speak a little loudly.
Yeah, louder. Yeah.
Yeah. Hello, sir. Sir, I have this question that you said that to better the resolution, we have to combine the two telescopes and to separate it by certain baselines. So how do we decide that baseline? What is the limitation for selecting that range of baseline?
Yeah. So of course, you know, when larger will be the baseline, yeah, higher will be the angular resolution. Yeah. Now, so if you have the technology, yeah, the best would be to try to get to the largest baseline. Yeah. And in radio interferometry, yeah, is what people have been doing. Yeah. Well, first they were using, you know, single radio telescopes on the ground. Yeah. And then, well, they decided to use radio telescopes on different continents, yeah, and even, you know, using a satellite, one antenna on a satellite, yeah, revolving around the Earth, yeah. So you see, well, largest is a baseline, yeah. More details you will get on your object, but the technology then is very, very difficult. In the radio, it's much easier, yeah, for many reasons, yeah. We'll come back to that much later, yeah. But at optical wavelengths, yeah, the problem is that to combine, yeah, your two beams, yeah, you need delay lines, yeah, because when you're observing the star, yeah, well, the star, yeah, is of course changing its position in the sky, and at the same time, the difference of length between the two beams coming from the two telescopes, yeah, is continuously changing, yeah, and you need to compensate for this effect, yeah, and to compensate for this effect, yeah, you need to use delay lines, yeah, which are extremely precise, yeah, well, mirrors set on the rails, yeah, and traveling quite fast, yeah, to compensate for this motion, yeah. And well, the longest baseline, as I mentioned, yeah, at the moment, yeah, are for the Shara telescope, yeah, in California, up to 400 meters, and they're very long baselines, yeah, and delay lines also, yeah, in vacuum chambers, yeah. So this is very expensive. At ESO, the baseline is of the order of 200 meters at maximum. So you need also long delay lines. And they, for instance, on the site of ESO at Paradise, it would not be possible, yeah, to install longer baselines because the top of the mountain, yeah, is too small. Yeah. So you see, so provided you have the technology and financial support, yeah, you would hope to go for a longer baseline because you get more detailed information, yeah, on all the objects that you're studying, yeah. But of course, you are limited, yeah, by the resources available, also by the technology, yeah, of course, yeah. Is it okay for you?
Yes, sir. Thank you.
Yes. Mm-hmm. Any other question?
Okay.
Well, I'm sure that we'll get more questions, you know.
Yes, I think some of them have.
Hi, Joe.
Yeah, hello Prakash, yeah.
Hi, this is Zamir here.
Jamir.
Oh, Jamir. Yeah.
Hi,
Jamir,
how are you
welcome.
doing?
Very
Hi.
fine. Very welcome.
So in radio, we use correlator, and in optics, we use these delay lines. Is there any technology which can compensate to overcome this delay line? And like
Yeah.
we use correlator in radio, right?
Yeah. You see, yeah, the nice things with in the radio, yeah, is that if you use you can use a coherent amplifier, yeah, to amplify the signal, yeah, at each single antenna while keeping up, you know, the phase, okay, of the electromagnetic wave, yeah. And this is fantastic, yeah. This makes life much easier, yeah. Now, in the optical wavelengths, yeah, or infrared wavelengths, yeah, well, there is no way that we can record, yeah, the electromagnetic field, which is oscillating, yeah, much faster, yeah. So if any of the participants would find a way, yeah, to record, yeah, with the phase, yeah, the electromagnetic field at optical wavelengths, yeah, you would get the Nobel Prize, yeah. So it would be a great idea, great achievement, yeah, yeah. So what we have to do, yeah, we cannot record the signals. We have to work, yeah, instantaneously, yeah, to let the two beams interfere, yeah. And we need we absolutely need the delay lines, yeah, right? Is it okay?
Yeah,
Gentlemen?
thanks.
Yes.
Yeah, thanks.
Yes. So
Okay,
indeed,
there
I
are-
mean, it would be
yeah.
great, yeah, if you know, anyone comes up, you know, with a nice proposition on how to amplify, yeah, the electromagnetic field created by optical light or infrared light, yeah, to record it with its phase, yeah. And then we could also use correlators, yeah, and everything would be so much simpler, yeah.
Okay, so there are a few questions here in the chat. For some reason, I think they're not able to ask them directly to everyone, but only to me.
Yes.
Okay, I've changed the setting now so that people can address it to everyone. But I can ask a few questions that are here. So Gaurav Banerjee asks if there is a graduate level book that you recommend for just introduction to interferometry.
Yeah, so the question is what kind of lecture I would recommend to?
Is there any graduate level textbook book that one can follow?
I think the most graduate level I know is the one I propose here with the lecture notes. Yeah, yeah. Unfortunately, because yeah, as I said, the two first lessons, yeah, would be sufficient for them. Yeah, because you don't need to go into the detailed mathematical details. Yeah, when you're at such a level. Yeah, but now, well, as you will, you know, improve your knowledge in mathematics, yeah, and have a good handle on integrals, Fourier transform, then you may go further, yeah. But no, not that I know, yeah. Well, of course there are, well, lecture notes which have been published after summer school, yeah, dedicated to interferometry, yeah. But immediately, yeah, it goes to a very high level, yeah. Well, the mathematics, yeah, always comes in, you know, very rapidly, yeah. So please just attend these lectures. Yeah.
Yeah. So the link to the lecture notes are also given in the announcements page in the course website, so you can check there. So Bikram Pradhan asks whether we can conduct an interferometry experiment with a light bulb instead of mobile phone flashlight.
I would say the problem, yeah, when you use a light bulb, yeah, usually, you know, it's a very, well, the light bulb, yeah, is a spherical shape, and maybe light is being diffused, yeah, from many parts. Sometimes it is opaque, then it won't work at all, yeah. So if you still have the chance, yeah, to have, well, maybe with a single LED, yeah, a single LED, yeah, set at sufficient long distance, yeah, would probably be sufficient, yeah. So single LED. The problem with the torch, yeah, that you buy, the flashlights, yeah, is that you have many LEDs, yeah, and that would not work, yeah. So you need a flashlight with a single LED, yeah. Or what else I'm thinking? Well, what would be nice, yeah? Sometimes you have reflective balls, yeah? I've seen many of them, yeah, at Aries in Italy, yeah? Well, they have this spherical metallic balls reflecting the light, yeah? Then you could look at the sunlight, yeah? Reflected by one of those balls, yeah? It's almost point-like, and this would be ideal, yeah? So for the PhD students, yeah, at Aries, yeah? So you know wherever you have stairs, yeah, you have these vertical metallic bars, yeah, with a ball, metallic ball, yeah, reflecting everything, yeah. It's like yeah, nice reflector, spherical reflector, yeah. Then look at the sunlight being reflected, yeah. Then it appears almost point-like, yeah. It's very bright, and this is the best you could use, yeah, during daytime, yeah. Otherwise, try to use a single LED, yeah, light, or anything which is bright but distant from you, so that it is seen as a point-like object, yeah. And then, well, what you could try also, yeah. Well, I didn't try it because I have no cell phone, yeah. So I'm very fortunate, yeah. Is to use your cell phone to record, yeah, some images of the interference fringes, yeah. And if you can do so, yeah, it would be nice that you pause them on the phone, yeah. I would be delighted to see them, and that you tell everybody how you did it, yeah. I have the good excuse that I cannot do it because I have no cell phone, yeah, and I'm so happy, yeah. Not that I cannot do it, but that I have no cell phone. Yeah. So next question.
Okay, somebody has raised their hand. Sorry. Could you raise your hand again? I think I somehow lowered their hand by mistake. Yes. Go ahead, ask your question. I think it's, if I'm pronouncing your name right, it's Dodi Thade. You can unmute and ask a question.
Hello.
Go ahead.
Okay, we can hear you.
Could you ask you are muted again. Could you unmute and ask a question?
Hello, I'm Daudi Tadei Mazengo.
Welcome.
Hi, go ahead.
Okay. I was very late to join, but I have a question regarding this interferometry. My question is, from after reading the lecture and all the materials, I understand that there will be a need of connecting several telescopes. Now, what is being considered in terms of the environment? Because with the number of telescopes, it means there will be a need of having a very large place, a very large land. So is this technology not considering maybe in minimizing the number of telescopes in order to make better use of the land?
Yeah, no, you're right. Yeah, if you want to install, yeah, an interferometer somewhere, optical interferometer, yeah, you need a flat area, yeah, with two telescopes. Now, well, if the longest distance between your two telescopes, yeah, is 10 meters, well, just do it, yeah. It will be equivalent, yeah, to the angular resolution you would get, yeah, while using a single dish telescope having a diameter of 10 meters. Yeah? it would be already fantastic. Yeah. Now, if you have a bigger land, yeah, just go for longer baselines. Yeah. But
Hello. Okay, thank you very much.
No, you're not audible right now.
yeah, someone muted me. Yeah.
Oh,
Yeah.
sorry. Yeah.
Yeah. No problem. Yeah. So, what could you hear from me? Because I don't know.
Yes, I hear you now.
Yeah. But
Just the last
yeah.
10 seconds.
Yeah. Oh, last 10 seconds. Yeah. So what I was just saying at the end, yeah, is that you can do interferometry while using a single dish telescope. Yeah. For instance, if you have a, you know, in your institution or observatory, well, even a 50 centimeter telescope or 27 centimeter telescope or 1 meter telescope, yeah, it's possible to set, yeah, a screen on top of your main aperture and to drill some holes, yeah? For instance, 2 holes, yeah, with a certain distance, with a certain orientation, and then you could use it, yeah, to try to estimate, yeah, angular diameters of planets, yeah, while observing Jupiter or Saturn, yeah, or, well, an asteroid or Galilean satellite, yeah. So it's possible, yeah, to use a single dish telescope, okay, with a dark aperture, but with holes being drilled in it, yeah, and just observe, yeah, the focal plane, yeah, the iridescent with the fringes, yeah, measure the visibility and make estimates of the diameters of those objects, yeah. So this is a very good, yeah, nice exercise, practical exercise, yeah, with students, yeah. So, well, in the past we were doing that every year, taking our students, yeah, where we had a single dish telescope, yeah, and then we just manufactured, yeah, some screens with holes, yeah, and well, if you're interested, yeah, during the following lectures, yeah, I will show how you could do that, yeah, because it's very nice and interesting.
Okay, thank you very much.
From where you are calling?
Oh,
which place?
I think I muted again. Sorry.
Okay. Yeah. So I was just curious, yeah, because I think it's a very long distance call, yeah.
Yeah.
I am calling from Tanzania.
From Tanzania. Wonderful,
Nice.
yeah.
Yes.
Very nice. Thanks a lot for participating. Very kind of you.
Okay, thank you.
Yeah, next questions. Do we have more questions now?
Pallab, do you have a question? I see you unmuted. Okay, there's a question from Vishnu Unni. What is the effect of aberrations of the telescope on interferometric measurements and how to compensate?
What is the effect, yeah, of the aberrations of a telescope, yeah, on interferometric measurements, yeah, right?
Yes.
This is the question, yeah. Well, I would say, you know, when observing with an optical interferometer, yeah, the field of view is extremely small, yeah. Well, typically at ISO, yeah, the field of view is even less than 1 arc second, yeah. So I mean, you're really observing, you know, near to the center of the field of view where you should have less aberrations, yeah, much less aberrations. So I would say, no. Well, even if you would have some aberrations, yeah, well, it would affect the iridescent, but certainly not, yeah, the fringe visibility, yeah, because the fringe spacing, yeah, just depends on the baseline, yeah, the distance between the 2 telescopes, yeah. But of course, I mean, you'd better have to, you'd better have, you know, a well-surfaced telescope, yeah, with a, well, as a small aberration as possible, yeah. But no, this is, I don't see it's a problem, yeah, yeah.
Okay, so Pallab, do you have a question? I see you unmuted, but we don't hear you. So in the chat,
there is a Hilbert's grade 8 of dimension 2. Was it off and on?
Ashwin? Okay, I think it
I
got
could not hear
unmuted
you.
by mistake.
Yeah.
The question from Pallab is, how can interferometer filter the destructive interference pattern?
How can it? How
How
can it
can
what?
how can interferometer filter the destructive interference pattern? I think we don't want to filter the destructive interference pattern.
No. I mean, are you referring to nulling interferometry, or I don't understand.
I think they mean how do we not have those minima, but I'm not sure. The person is unmuted, but we cannot hear.
Yeah.
Can you clarify the question better, Pallab? Okay. In the meantime, we'll take a question from Sarvesh Gharat.
Hello, sir. Am I audible?
Yes, you are. Go ahead.
Sir, as we have discussed that two telescopes are kept at distance b with respect to each other. So won't atmospheric conditions at every individual telescope take a picture or take a role in this? Like, won't it affect?
Yeah. So this is an important question. Yeah. So the question is, when you have two individual telescopes, yeah, you have of course seeing effects, yeah, which are different above the two apertures. Yeah. So how do you take this into account? How do you correct for it? Yeah. Now, yeah, the first thing you need, yeah, when you have a big aperture, yeah, two big aperture, you need adaptive optics, yeah, okay, at each aperture, yeah, to correct for the atmospheric, yeah, thing, yeah, just above the two apertures. So you need adaptive optics. This is absolutely necessary. And now there is still a problem, yeah, is that the optical thickness, yeah, of the atmosphere above one aperture may be different from that above the second aperture, yeah, and this you cannot correct with adaptive optics, yeah. So what will happen, yeah, is that when you will be looking at the fringes, yeah, in the focal plane, the fringes, yeah, will be traveling, in an erratic way, yeah. But now you would like to integrate the fringes, yeah, the light of the fringes. So how do you do? Well, what you need to do is to track the fringes, yeah. So fringe tracking, yeah, is necessary, and well, it's one of the very important subsystems, yeah, of an interferometer, and where you need a very fancy algorithm and a nice technology to be able, yeah, to follow the fringes, I would say with a speed of the order of the millisecond, yeah, right? So you need a fringe tracker. So you need adaptive optics above, yeah, each single aperture, and after you need a fringe tracker to follow the erratic motion of the fringes because of the varying, yeah, thickness of the atmosphere above the two apertures. But we'll come back to that, yeah, later in the next lessons, yeah. So we have to go slowly, yeah. Don't ask too many specialized, difficult questions now, because, well, as we shall progress, yeah, you'll get the answer to some of your questions.
Okay, so thank you.
With pleasure.
Okay, Desh has a question. Desh,
So I just had a
ahead.
comment on the question that was asked about the destructive interference, how that can be avoided. And I think the person himself or somebody else has responded in the chat about it. But I just want to add that the pattern, interferometer pattern itself, is a manifestation of the constructive and destructive interference. The situation changing as a function of angle, and those are essential part of the interferometric pattern itself.
Yeah, you don't want to get rid of the dark fringes, because otherwise you will not see the bright fringes. Yeah, so it's just interference. Yeah? You have to work with that. Yeah, sure. Another question?
Yeah, there are a few more in the chat. The base from Ankur Ghosh, the baselines of optical interferometer can change with different frequencies or it is fixed.
So, well, I shall repeat the question to make sure that I understood it well. Yeah. So,
Sure.
can you say, can the baseline, yeah, between the two interferometers change with the wavelength, right?
Yes.
Yeah. Okay. Now, well, the baseline, yeah, usually you fix it, yeah, during the night. You don't change your baseline, yeah, but you may change the frequency, yeah. And while changing the frequency, you remember that the interfringe separation is lambda over D or over B, where B is the baseline, yeah. So you see that while working at shorter wavelengths, yeah, you will get, yeah, separation in the between the fringes, which is smaller, yeah, since it's proportional to lambda, yeah, and you'll improve the angular resolution of your facility, of course, yeah. So, I mean, but as you know, yeah, the physical properties of the stars, yeah, may be different at different wavelengths. So it's very interesting, yeah, to indeed, yeah, get information about the fringes, yeah, at over a wide range of wavelengths, yeah, coming from blue light, yeah, to 1 micron, and this is well frequently achievable, yeah, with the Shara facility, yeah, in California, while at ESO, yeah, specialized just in the near infrared.
Okay, so the next question is, let's see, is the point spread function obtained by each telescope individually or is it obtained using all the telescopes?
Yeah. Now, well, usually you agree that if you look here at the VLT here, you see that you have 4 VLT, big telescope, yeah, big aperture, yeah. And so the area disk of each of these 4 telescopes is the same, yeah. So when you superimpose, yeah, the 4 of them, yeah, the focal plane, yeah, well, they are just similar, no problem. You could do the same with the auxiliary telescope, yeah. So you see, well, you see a small one of the auxiliary telescope here, but there are in fact 4 of them, yeah. And you do the same. You only work with the 4 ATs, yeah. Now, when you work, yeah, you combine one auxiliary telescope, 1.8 meter diameter, with a VLT, 8 meter diameter telescope, yeah. The situation is more complex, yeah. So the combined, yeah, area disk will be different, somewhat different, and this is something nice, yeah, that we will do later in the context of the exercises, yeah. So you should try to contribute to that, yeah, in the future. And we would see, yeah, what happens when we combine, yeah, a small aperture with a big aperture, yeah. How does it affect, yeah, the combined area disk? How does it affect, yeah, the contrast of the fringes, yeah? Well, now I can tell you that at ESO, they never combine, yeah, a small aperture with a big aperture because, well, there are problems, yeah. It's more, there are difficulties, yeah. But in principle, it's possible, yeah. And well, I will propose an exercise, yeah, in that context because, well, it's interesting, yeah, to see whether we can do it or not. And even while using a single disc aperture, yeah, you could make a screen covering the whole aperture with 2 holes having different sizes, yeah? So for instance, a 1 millimeter hole combined with a 3 millimeter diameter holes and see what happens, yeah? So it's possible to address that problem, yeah? From a practical point of view while playing with a telescope or numerically, yeah? While making some well, practical exercises, yeah? But it will be interesting. Yeah.
Okay, I think this also answers question asked by Suman about different aperture sizes, aperture telescopes, whether they can be used for interferometry.
Yeah, but you will see, everybody will feel a lot of excitement, you know, when you will construct your own milli interferometer and play with it, yeah? Because, well, this is the subject of the second lesson, yeah? So I should not tell too much today, yeah? I let you the time, yeah, to visualize, yeah, the second lesson and then second lecture, and we'll discuss it next week, yeah?
So a question from Gino, is the angular positions of the telescopes with respect to each other in interferometer relevant? I think they mean the 2D, two-dimensional distribution of the telescopes that are part of the interferometer.
Oh, I mean, I'm not sure I fully understand the question, yeah, but now, well, what happens, let's assume that you are looking at the star at the zenith, yeah? So just at the vertical direction, yeah? Just go on the star and look at the interferometer, yeah? You'll see, yeah, well, all the single aperture with a certain separation, which is a baseline, yeah? Now, let's assume that you observe the same star, yeah, 4 hours later, yeah? So of course, it's, you know, the rays now get inclined, yeah? And if you are at the position of the star and look at the interferometer, yeah, what you will see is a projection, yeah, of the position of the 4 telescopes, yeah, on a plane perpendicular, yeah, to the line of sight, yeah. So there is a cosinus theta or cosinus z, where z is the zenith distance, yeah, which comes into play, yeah. So in fact, the baselines, yeah, the length of the baseline change as a function of time when the star, yeah, passes from one position of the sky to another position, yeah. And this is very nice because thanks to the rotation of the Earth, yeah, you may cover, yeah, quite a nice range of baselines as a function of time, yeah. But we'll come to that later, yeah. So nice question, but you will see during the course of the lectures, yeah, you will get a more precise understanding of this, yeah.
So Rashmi Ranjan has a question. What is the limit of baseline that we can ever achieve?
Well,
I guess, right.
Yeah, the limit, there is no limit if technology allows you to do anything, yeah. And well, there were, for instance, very nice space projects, yeah, to build up, you know, interferometers in space, because there it's very easy, yeah, to get very long baselines, yeah. You may set, yeah, to satellites, yeah, to telescope, yeah, very far away from each other, yeah. And there have been projects already, yeah, to set up, you know, the space interferometers with baselines of tens of or hundreds of kilometers, yeah. So, but you know, it will be much more expensive, technology from a technological point of view, yeah, very much more demanding, yeah, and costly, yeah. So this is always a real limitation, yeah. So well, I'm always in favor, yeah, of trying to do the best, yeah, with minimum investment, yeah. Well, as an example, yeah, at Haute-Provence Observatory in France, yeah, they had a 1.9 meter telescope, yeah, and everybody was almost convinced that, you know, it's useless now to have such a small telescope compared to the big telescopes, yeah, which are rising everywhere, yeah. But well, some people, yeah, really tried to maintain that telescope in shape, yeah. And the first exoplanet, yeah, 51 Pegasus B, has been discovered, yeah, with this small telescope, well, 1.9 meter size telescope, yeah, by Michel Mayor, yeah, and his collaborator, yeah. And this shows that, you know, with, well, not very expensive facilities, you may do excellent work, yeah, very innovative, yeah. You need ideas, yeah. So therefore, I mean, even in the course of these lectures, you know, with you will see a minimum amount of equipment. Yeah, you may do wonderful things, and maybe there are things we didn't think yet about. Yeah, what we could do. Yeah, and in that respect, I will show. Yeah, this will be in 3 or 4 lessons from now. Yeah, how in my university, yeah, we design the smallest optical interferometer ever built up, yeah, to measure the angular size of the sun, yeah. So amazing. So there is a lot of rooms, yeah, for new ideas, new propositions, yeah. Don't think that, big investments are always needed, yeah, to reach, fabulous results, yeah. Yeah, I'm personally not convinced at all, yeah, yeah. So a lot of good science, yeah, can still be done, yeah, with, let's say, small facilities, moderate facilities. Yeah. Okay, next question.
Vishnu only wants to ask a question. I'll unmute him. Go ahead, Vishnu.
Yeah, hello. Am I audible?
Yes, you are.
Yeah,
John, you can hear him, right? Go ahead, Vishnu.
yeah. So as we said, the baseline is the separation between two telescopes, right? So in that, so in the first place, when we have a single telescope, it's lambda by d, where d is the diameter. So when we consider two telescope, like in the diagram you showed that it's the distance between center of one telescope to the center of the other telescope. Should it be that way, or the extreme end of the left telescope? I mean, the extreme left end of the left telescope and extreme right end of the right telescope, something like that.
I see what you mean. No, the separation between the fringes will be really lambda over b, where b is the distance between the two centers of the two central pupils. Yeah, okay. And now you see that all the fringes, yeah, have a certain width, yeah, and the width, yeah, well, we'll make those calculations, yeah, but well, to answer your question, no, is really the b the distance, yeah, between the two center of the two telescope, yeah, or between the two left side of the telescope or the two right side of the telescope? It's always b. It's really b, the baseline, yeah.
Okay. Okay.
Okay, so we have quite a lot of questions streaming in, but we are already about 10 minutes past the time. Should we defer these questions to the forum or the next time?
So I propose that we still go on for 5 minutes, yeah, and then we postpone the next questions, yeah, for the next session, yeah, because otherwise there will be no question during the next session, right?
Yeah, sure.
5 minutes.
So some of them are very general. Let's see. There's a question by Mengkyun Zhao. Could you please compare the difference between radio and optical interferometry? I guess if these sort of questions are already answered in the lecture, if we could just...
Yeah, right, yeah. Well, I already gave some answer, yeah, to that question, yeah, by saying that in radio, yeah, while using a coherent amplifier, yeah, you may, yeah, amplify the signal and keep the phase information, yeah. This you cannot do at optical wavelengths, yeah. Okay, so this is a big difference, yeah. Now also the big difference between optical and radio interferometry is that when you combine the light beams, yeah, coming from two apertures, yeah, optical wavelengths, yeah, you should make sure that the difference between the lengths, yeah, coming from the star, yeah, to the focal plane along one of the beams and along the second beam, yeah, that the difference is less than a few microns, okay, at optical wavelengths. Now, if you go in the radio, well, this limitation, yeah, is something of the order of, well, sometimes a few centimeters, yeah. And from a technological point of view, yeah, it's much easier, yeah, to achieve such a tolerance of a few centimeters than a few microns, yeah. So these are the biggest difference, yeah. So especially the fact that we cannot record light information, yeah, and use later on, yeah, correlators, yeah. So this is the biggest difference between the two.
Okay. Some of these are more general. I think we can answer how PSF can be defined.
How to define the PSF, yeah, right?
Yeah, yes.
Yeah, yeah. Okay, of course, I mean, this will be the subject, yeah, of a next, not the next, but the fourth lesson, yeah. We will establish the expression, yeah, of the point-spread function, yeah. But well, in fact, yeah, it's first-order Bessel function, yeah. So it's not that easy. What we'll do before you know, going to such a technically detailed, yeah, derivation, we'll take an aperture which is not circular, yeah, which is square. So square aperture, yeah, are more easily manageable, yeah, from a mathematical point of view. And then you would see that the function defining, yeah, the point-spread function, yeah, is, well, a sign cardinal, yeah. Okay, now, more simply, what is a point-spread function, yeah? Well, the point-spread function, yeah, is the image you get in your focal plane when looking at a point-like star, yeah? So I remind you that it's not a point, yeah? It is a dot of light, yeah? A dot of light, which is a special shape, which is the airy disk, yeah? And during the next lessons, yeah, we will establish the expression, yeah, of this famous airy disk, yeah, which is a first-order Bessel function, yeah. So from a technical point of view, it's not easy, but if we would consider, yeah, a square aperture, yeah, you will see that it's not anymore, yeah, a first-order Bessel function, but it's a sine cardinal function, yeah. Sine cardinal is sine x divided by x, yeah, much more simple. But we will establish those expressions, yeah, during next lessons, yeah. But remember that, well, a point-spread function, yeah, is just the image you see of a star in the focal plane of your telescope, yeah. Now, if you have a small size telescope, yeah, well, the angular size of the dot of light will be very wide. If you have a big size telescope, yeah, well, the angular size, yeah, will be small and will provide, yeah, a much finer angular resolution, yeah, to your telescope. Okay.
There's a lot of discussions going on here at the chat window too. I think you guys should do it more in the forum so that there's a permanent record and people can view it at their own time.
So Prakash, yeah, maybe can you yeah, explain, yeah, with maybe more details to the participants, yeah, how they can go, yeah, to that forum and continue the discussions there, because, well, it's very interesting, yeah, sure.
Sure. Okay, so I think most of you who are on this call right now would have already created an account at the nrc.iuca.in portal, and also self-enroll yourself in the course. If you go to the main course page, you will see a listing of all the topics that we have with video lectures underneath, and some of them, as we go along, we'll add more modules to it. But at least the first lecture, you'll see that it has a forum specifically for discussion. And you can add the questions that you have about the first lecture in that forum. And it has this option where if you just go to the left of the title, there are two arrows that you can use to upvote or download, just like Stack Exchange or Reddit. Or any of the sites where they allow voting of questions. This is just, I mean, this is not going to count towards a grade or anything. This is just to make sure the questions that a lot of people have gets addressed with priority. So if you have a question, go ahead and post it over there. If you see it's already been asked, just go and upvote a question or answer over there so that we know we can, you know, filter out the questions that needs to be prioritized. If you have any other questions, you can always, there's also a general information forum that is just below the announcements in the top of the page. That is generally to understand how either the course works or the portal works or any other general questions that you might have. Okay.
Yeah. And we also invite the participants, you know, who want to provide some answer to some of the questions, yeah? If they feel there's a good answer, yeah? Just please go ahead, yeah? And please just read the guidelines, yeah? before getting into the forum, yeah, just to make sure that the content, yeah, everything what will be well published on that forum, yeah, is well behaved, yeah. Well, this is obvious, yeah, but
Right.
just
Please
remind me.
make sure you make good use of the forum. Just like I can see already in the chat that you guys are quite active. So make sure you keep the same thing in the forum over there. And we'll regularly meet like this live, and we'll be discussing some of the questions that require more elaborate answers and so on.
Yeah, Rakesh, I'm just hearing a bird singing, right? Is it on your side?
Might be. I just hear crows, but.
Oh, yeah.
Oh, that's from me, Jean.
Participating crow to the forum. Very nice.
Okay, go ahead.
Yes, Jean, thanks very much for a fantastic beginning to the series, and to Prakash for coordinating it. And you participants, see many of you have been very active in the chat window. Thanks to all the participants. And I also would like to record my thanks to our IUCA Computer Center colleagues who have been working behind the scenes to make sure everything goes smoothly, particularly Sagar, Santosh, and Yogesh. And also thanks to Desh, which I forgot to mention in the beginning, but Jean mentioned it, that he will also be part of the course and give a set of lectures, or a few lectures on Fourier transforms, which are so integral to actually interferometry and imagery construction. So thanks very much to all of you. And we meet again on next Monday, same time. And for lectures, we will sort out the time and schedule, and Prakash will announce it at due course. Okay, thanks very much. Thanks a lot to all of you.
Yeah, thanks. Okay, bye-bye to everybody, and see you next week. Bye.